Hello everyone, my name is Milan Zheng from Nuvoton Microprocessor Division. The topic to be presented today is the introduction of MCU security. Regarding MCU security, we will talk about the target of MCU security, type of attack, how it functions, used to prevent attacks, and the recommendations for MCU security architecture. This time, I am going to introduce the second session, types of the attack. This session will talk about the classification of attack methods against MCU, and let you further understand the methods used in these attacks by introducing a few examples of attacks. The first one to introduce is software attack. Software attacks use security vulnerabilities in the subroutine, protocols, or encryption algorithms to control the system or obtain protected data. This is an example of a stack overflow attack. When Nuvoton calls echo subroutine, the memory distribution will be as shown in the figure, including core region and the stack region. In core region, the main routine jumps to the echo subroutine through the branch and the link instruction. When entering the echo subroutine, an 80-byte local buffer and a return address will be set in the stack region. This return address points to the next instruction of branch and the link in the core region. Before the echo subroutine ends, the return address will be fetched from the stack to return to the main routine. If a function guess does not check the length of the input string, it will become an exploitable attack vector. Potential attackers can enter a piece of malicious code and an incorrect return address. Since guess does not check the length of the input string, the wrong return address will override the original correct return address. This wrong return address points to the malicious code itself. After echo ends, it will not return to the main routine, but will jump to the malicious code. In this way, malicious code gains control of the program, which may lead to the confidential data leakage, or improper operation, or other errors. This is the method of exploiting software vulnerabilities to attack. Another common attack in network applications is the man-in-the-middle attack. Let's use the figure below to illustrate. Suppose Alice and Bob want to encrypt data sent over the network. Then Alice and Bob need to exchange each other's public keys first. Alice first sends a message with the public key to Bob. At this moment, a perpetrator appears. The perpetrator intercepted the message sent by Alias, replaced Alias' public key with his own public key, and then sent the forged message to Bob. Bob's reply message will be sent back to the perpetrator. After the perpetrator takes out Bob's public key, he replaces Bob's public key with his own public key, and then sends the forged response message to Alias. After that, all messages sent between Alice and Bob will be obtained by perpetrator. If the denial of the network protocol is fraud, perpetrator can use interception and the counterfeiting techniques to make users at both ends of the network connection think they are communicating with the original user. In fact, all transmitted messages will pass through the perpetrator. This is the attack method that exploits vulnerabilities in software protocols. Non-invasive attacker, which is a hardware attack, There are two common non-invasive attacks. One is void injection attacks. Void injection attacks inject voltage or clock glitches, causing unexpected errors when the MCU executes instructions or reads and writes registers and memory, finally leading to incorrect execution results. Take the voltage glitch as an example. Connect a MOSFET switch between the VCC and the ground pins of the MCU, and use a GPIO output to control the MOSFET on and off. When the MCU is executing, the program will output GPIO signals at the selected position to turn on the MOSFET switch, and then connect VCC and the ground, and generate glitches of VCC. If you check the captured VCC signal, you can see that the VCC is jittering. VCC jitter will cause propagation delay inside the MCU. Simply put, there will be signal delays in the logical gates inside the MCU. Signal delay may cause the clock and the read and write signals to be out of sync, leading to register write errors. This attack method can be used to tamper with trust zone settings. Trust zone's secure wall and the non-secure wall are set through two system components. One is IDAU, and the other is SAU. IDAU is a hardware setting and cannot be changed. For example, IDAU of M2351 uses the 28th bit of the address to distinguish secure and non-secure wall. If the 28th bit is 0, the address belongs to the secure wall. Otherwise, it is a non-secure wall address. For the code region, the 256 MB of the low address is secure, and the 256 MB of the high address is non-secure. SAU is software programmable. The program can configure the secure wall and the non-secure wall by writing to the SAU registers. The security attributes of an area will be compared with the settings of IDAU and SAU. If the two settings are different, the higher security setting is used as the security attribute of the region. For example, there is an area where IDAU setting is non-secure, while SAU setting is secure. After comparisons, the attribute of this area will be secure. The figure on the left shows the settings of IDAU and SAU. The security attributes after comparison are shown in the figure on the right. After setting the security attributes, write a data in the secure region called secret. The value of its 28th address bit is 0. From the perspective of the CPU, the location of the mirror address, that is, the 28th address bit is 1, can also be regarded as having a secret data. Since these two addresses belong to the secure wall, the code in the non-secure wall cannot read the value of secret. If a VCC glitch occurs when setting the SAU register, the writing of the SAU registers may fail. The security attribute of the code region will be set as the default value by IDAU. At this time, if you write a secure data in the secure wall, the mirror address of the secure data seems to fall in the non-secure wall. Therefore, the value of secrets seems to be readable by non-secure code. In fact, there is a flash memory controller which manages all flash access. For the non-secure code, it can only read the flash memory whose M28's address bit is 1, but cannot read the flash memory, whose 28th address bit is 0. Therefore, this secret data will not be read by the non-secure code. This fault injection attack is to use VCC glitches to cause the write errors of the registers, making the protection function ineffective. Another common non-invasive attack is Sidechain Oil Attack. Sidechain Oil Attack uses an oscilloscope or other measuring instruments to monitor the signals generated by the MCU when performing encryption and decryption operations. The signals include timing, power consumption, or electromagnetic emission, and so on. The captured signal data will be input into the pre-established statistical analysis model to derive the encryption key. This is an example of correlation power analysis, which uses chip whisper light to measure power consumption. The PC side runs the chip whisper light applications. One is a signal capture program, and the other is the power trace analysis program. And there is a M2351 testboard, which runs the AES encryption program. The encryption key and the random plain text are sent from PC to M2351 testboard through the chip whisper light. After receiving the data, M2351 starts to perform encryption. At this time, chip whisper light uses its ADC pin to measure the power consumption change of the M2351 LDO pin. Once the encryption is done, M2351 sends the ciphertext to chip whisper light. Then chip whisper light sends the ciphertext and the major power consumption signal, which are also called power trace, to PC. In this experiment, the analysis program of chip whisper light used the method of correlation power analysis. The analysis program needs to establish a reliable power consumption model in advance. In the analysis process, the AES 128-bit key is divided into 16 bytes, and each byte is regarded as a subkey. The captured power trace is calculated together with the power consumption model to derive the most relevant coefficients. In theory, the more power trace captured, the more accurate the derived correlation coefficients. The results of these experiments are listed in the table. In the analysis of 200,000 power traces, 7 of the predicted subkeys are consistent with the encryption key. When 600,000 power traces were captured for analysis, the number of correctly guessed subkeys increased to 10. This Sidechain Oil Attack captures the physical characteristics generated when the MCU performs encryption or decryption, include timing, power consumption, or electromagnetic emission. Then compare and analysis with the pre-established model to derive the encryption key. The last type of MCU attack is invasive hardware attacks. This kind of attack will destroy the function of the MCU and cause irreversible damage to the MCU. Invasive attacks are usually divided into 2 steps. The first is to destroy the package of the MCU and use chemical agents or physical means to remove the package on the chip. Then, use the microprobe to measure the signal on the MCU internal bus during operation to obtain confidential information, or use the FIB method to modify the MCU internal circuit and turn off the MCU protection function. This invasive hardware attack requires sophisticated and expensive instruments. In the past, it needed to be done in a professional laboratory, but now there has been a trend of renting out such expensive tools. Therefore, for MCU, the threat of invasive hardware attacks will be greater than ever. In the previous, 3 types of MCU attacks were introduced. They are software attack, non-invasive hardware attack, and the invasive hardware attack. Comparing the manpower, time, and the money required for attacks, software attacks are the lowest, followed by non-invasive hardware attacks, and the invasive hardware attacks are the highest. The y-axis in this figure represents the cost of the attack, and the x-axis represents the cost of the security function denied. If the value of MCU assets is represented by a slash, when the assets value is high, potential attackers are more likely to adopt more costly attack measures. At the same time, the denied cost of MCU security functions also increase with the increase in attack cost. In theory, no security function absolutely secure. Under attack at all costs, there will always be a day of cracking. Therefore, what the successful MCU security function wants to achieve is a relative protection. Like this, the value of the assets protected by the security function will be lower than the sum of the time, manpower, and the resource spent by the attacker when the attack is successful. The above is the tutorial video. Thank you for watching. Welcome to subscribe to our channel. If you want to know more information, please contact us.